Good to go? Okay. Hello, everyone. Thank you all for being here. It's such a beautiful day. As you may know, I'm here today to talk about this particular paper titled as Word2Bits, Quantized Word Vectors. That was published almost exactly a month ago on arXiv, and it's authored by Maximilian Lam from Stanford University. But before we get into the details of the paper, just a bit of an introduction about myself. I graduated from my PhD program at Western about 2 years ago. When my PhD was in computer science, and I was particularly focused on natural language processing and social media analytics and mining. And as part of my PhD, we closely worked with a medium-sized company here in Toronto called InfoTrellis to automatically detect and identify privacy preferences of social media users whose data is publicly available. And just a few weeks before my graduation, I joined TD as a data scientist, and I was at times a data engineer at TD. And we worked on a customer 360 platform, and also we did some Twitter analysis and mining. Then I joined Zero Gravity Labs, the innovation arm of Loyalty1. And there I was involved with 2 projects. The first was heavily research-oriented, and we kind of tried out a variety of text classification methods, starting from conventional NLP methods to a state-of-the-art of deep learning on top of chat data from call center of air miles. And also we tried out a lot of different ways of representing text and kind of came up with this report for the main office at Loyalty1 to rely on when they're deciding about different representations and different models and techniques. And also we tried on a different project, we tried adapting embedding methods similar to WartoWhack, GLOV, from NLP on top of transaction data from Metro, Rexall, Sobeys that Air Miles has, and we tried to come up with product embeddings based on the baskets of products that people purchase. And it turned out that those vector representations were able to capture a lot of effective and important information about those products, including product category, for example, and also the seasonality of product, similar to what word embeddings are capable of in the NLP domain. They capture a lot of syntactic and semantic regularities of text and these words. About 5 months ago, I joined Microsoft Canada, and our team is helping Microsoft Azure's clients, a lot of clients, to solve, kind of develop and deploy their AI and data science projects on Azure platform. So let's get started with the paper itself. So the whole purpose of this paper is to come up with quantized versions of word embeddings. And the main motivation here is that these vector representations generated from these algorithms, again, GLOV, Word2Bits, doesn't matter, FastFix, whatever the method is, these vector representations take a lot of space. So typically they have 300 to 500 dimensions, and each of these parameters and dimensions is a full precision floating point, taking 32 bits. And we have millions and millions of words that we want to have these vector representations for. So on average, they would take about 3 to 6 gigabytes of memory and storage. Well, of course, as long as you have the cloud, who cares, right? You push the compute, you push your data to the cloud, you easily access it through a REST endpoint, and that's it. But let's say you don't have web connectivity or the means to access the cloud, and you really need these vectors to be, let's say, on a mobile device or an edge device in an IoT setting. Then that's a huge problem that you're facing here. But before getting into the details of the paper itself, let's take a look at what has been done in this area. So a lot of people have proposed adding extra layers after these vectors are trained to compress the representations. For example, people have tried dimensionality reduction methods after these vectors are trained and prepared. PCA, TSNE, whatever you want to try out would do the job, would compress these representations for you. Also, people have tried pruning the vectors. And deep compositional coding is another approach that is kind of the state of the art and is more recent, and is based on the idea that some words, like for example dog and dogs, are very similar in terms of what they mean, but just the difference is that one is plural, one is single. So we don't really need to have two unique vector representations for the two, and they can actually partially share some parts of these representations and that have this additional parameters and dimensions to differentiate between the two, right?
Well, what about queen and king? I mean, it's similar. It's just the gender.
Yeah, the same. It's the same idea. So if there is, I don't know, if, for example, there is a syntactic parser for you to tell that these two are the same words, one is plural, one is single, then you can encode that into the vector representations. Also, if there's an ontology that would give you this information that queen and king are pretty much the same without this particular difference, you can make use of that to compress the vector representations. As long as you have that knowledge somewhere externally, then you can make use of that. Right? The problem with these approaches is that often you need to retrain these embedding algorithms just to apply them on a different domain, a different context, for example, what we did at Zero Gravity Labs. And having this extra layer of compression is just an additional computational layer added to your model. And it adds to the computational complexity of the model, and now it's more intensive to run the training first and then to have this additional layer on top of it to compress the vectors. And also it degrades the accuracy of the model because you are cutting some data out of your vector representations. You're just taking some data out after it's already trained. So some other approaches are focused on learning these high quality representations directly in the training phase. And they try to keep them contact as they're training rather than having this additional layer of compression after they're trained, right? So network pruning have been used as the simplest approach. These techniques would just take out that connection with its weight below a particular threshold and just they retrain that neural net again. Deep compression, the same technique that I just talked about that would partially share some parts of these representations, have also been introduced at the training phase. And of course, quantization have been used. And there are two broad categories for quantization to compress these vector representations in the research. The first one is physical quantization, that you would train the neural net with low precision floating points and arithmetics. And the second one is virtual, when you would train it with full precision floating points and arithmetics, but you would have constraint values at the end. And this paper falls under this particular category. So they train the model in a regular way, but they try to have constraint values as a result. And we'll see how they accomplish this. But before we get there, just a very quick recap on Word2Bits, because this model is heavily focused on continuous bag of words. So Word2Bits, as you already know, has two different flavors, two different architectures. One is the skipgram model, in which you predict the context words given the target word in a certain window of words. And for continuous bag of words, it's the other way around. So you try to predict the target word given the bag of words from the context. So one is the inverse of the other, and choosing in between the two may seem arbitrary, but they are statistically very different in the sense that continuous bag of words smoothes over a lot of distributional information of words here when it considers all of that bag of words representation along with the target word as one observation. Whereas in the skip-gram model, you have each context target, context target, context target. Each of these is a different observation. So you're taking into account a lot more of the distributional information of the words from your corpus. Okay? Because of that, continuous bag of words works a lot better with the smaller data sets. Whereas the skip-gram model works a lot better when you have a large corpus, because you can actually rely on that fine-grained distributional information of the words. So the paper focuses on continuous bag of words with negative sampling. And just again, a very quick recap for negative sampling: when you pass each training sample through your neural net and you want to modify the weights, you only modify the weights of a very small percentage of your negative samples, meaning that a very small percentage of the words that are outside of the window of the words that you are taking into account. Okay? So let's take a look at the continuous bag of words loss function. So here for the loss function, we have U of O, which is the vector representation of the center word we are trying to predict in the position O in the text. And VC hat is actually simply the average of all of the vector representation of the context words. So you have here VI as the vector representation of the context word, and W is the window size, the hyperparameter that you tune. And for all of these context words, you just compute the average of the vectors. So that's it. Okay. And then here, let's focus on the first part. What we want to do is to kind of maximize the dot product of UO transpose and VC hat. Why? Because this is a vector representation of the center word in the window we are focused on. This is the average of all of the context word vectors. And the dot product is kind of a measure of similarity and relatedness between two words. And that's what we do in the skip-gram model too. We're trying to maximize this measure of similarity between the word and the words that appear in the same context as that word. So the sigmoid of that would also be maximized, the log would be maximized, and we have this negative sign here to make it a minimization objective. For the second part, we are including the negative samples. K is the number of the negative samples we want to update the weights for. And it's the very same, except here we have a negative sign here, which makes sense because now you want to have this minimized. You want the words, the vector representation of the words that appear outside of this context not to be similar with the ones inside this window. Okay, so based on this intuitively, this loss function makes sense. And once you have this, you calculate the derivatives, and you update all of these vector representations for the center word in the position O, for all of the center words that are outside of this window of size M, and all of the context words inside this window of size. Sorry, here it's actually window of size W, not M.
So you choose UI. How do you choose the UI?
Can you repeat the question?
Yeah. The question is, how do we choose UI? So at the very, very beginning, it's just a random assignment to a vector and until it converges.
So
Okay.
VC is for each word specific?
VC hat or VC itself?
VC hat.
VC hat is the average of all of the vector representations of the words in the window.
And then it's for each window specific.
Yes.
for each word specific, and then you can do that.
Yeah,
So for each window for each word. So we
You'll choose one window size when you're training a model, so W will be fixed.
yes. And then you have a specific VI for each word, and then you average. You calculate the average of all of the VIs in the window you're focused on right now, in your current window.
Does it make sense to have a variable context? Did anyone work on this?
I haven't seen anyone working, and I can think if someone would want to do that, there should be a good reason why this, for example, context is smaller in this particular part of the text and why it is larger in this particular. Coming up with a random window size, I'm not sure if that would be feasible. But yeah, I haven't seen anyone.
So if you enlarge the context window as much as possible, it's basically going to be very similar to LSA, latent semantic analysis. So the point of word vector, I'm sorry to interrupt.
No, it's okay.
The point was to reduce this window size so the computation is compressed from the beginning, as opposed to having your entire text and then trying to find what co-occurs with what, then get word vectors for as with other methods.
Yeah, I think the question though is that have anyone tried to have W being a variable?
Yeah, so there is actually variable skip graph methods that you sort of jump over some words based on their tags or based on their types, but they're for the specific purposes. Usually normal word vectors use every word in context.
Okay.
Google after variable skip graph comes.
So, good till here? Should I move on? Okay. And okay, so for every single word, we have two different vectors. Okay. One vector is for when that word is actually the center word, and the other one is for when that word is actually a context word. So once all of this process is done, finished, they just sum these two up, and this is the vector representation of word I. Okay.
People try to concatenate those two vectors?
I'm assuming people have tried it. I'm not sure if it worked better. I haven't really seen the concrete examples, but I guess people have probably tried it. So what they do in this paper, they introduce a quantized function, qvex, that you can pass the vector representations into and get a new vector representation that would be compressed to a particular bit level. So it can be q1x, q2x, depending on what you want. And what they do is to simply pass each of these vector representations into this function. So there's nothing more than that. And that's what they do in the loss function too. Okay, so if you look at it, it's just passing each of these vectors for the center word, context word, negative samples into this function. Okay. And how they come up with this Q is actually very experimental. They tried out different discrete functions, and then they decided that these two worked reasonably well.
Okay.
Yeah. So for 1 bit, they introduced this particular discrete function, and for 2 bits, there's this other function. Purely experimental. Okay. And the issue here is now once the training samples are passed and you want to calculate the derivatives in your back propagation, the derivatives are either 0 or undefined for these discrete functions. And what they do, they rely on Hinton's straight-through estimator. This is something that Jeffrey Hinton only talked about in one of his videos in the neural net course he has in Coursera. And he says this is an unpublished work, but for discrete functions, you can assume that the derivative of that function is actually an identity function.
So isn't X a vector?
Each parameter of the vector.
Okay.
Okay.
The identity kind, why do you think that doesn't make sense?
I will refer you to his video. So that's what they did. They calculated the derivatives. And actually, there's no published, even though that video is old, there is still no published work on this.
It doesn't make sense.
These are postulates.
Oh, I see.
You have to accept them.
Yeah, and that's actually what that video is what this paper cited for the use of this.
So, yeah, I thought just citing the archive was bad enough, but now citing the
Of course,
Yeah, it's actually
So the derivative
Coursera
of
that they
Q
cited.
Level X is X.
Yeah.
Good.
So that's that's how they calculated the derivatives. They came up with these quantized vector representations, and they started evaluating them. So they ran a lot of intrinsic experimentation on the similarity and analogy tasks with full precision vector representations with different dimensions. Thresholded actually means they trained it the regular way, and then they applied that quantization function on top of the trained vectors. And the quantized version is what I just talked about. During training, they just pass those vector representations through those quantization functions, and that's how they actually train. And for word similarity tasks, they tried out a lot of different data sets. And for almost all of them, the quantized vectors are doing better than the other versions of these vector representations. And these are actually the correlations between the similarity rankings that these vector representations gave them compared to rankings that humans came up with in these data sets. Okay? And they also tried it on word analogy tasks, where you would say A to A prime is similar as B to B prime, and you try to predict B prime automatically. There are two data sets for these tasks, one from Google, one from Microsoft Research, and there are two different ways that you can predict that using the vector representations. They use both data sets, both approaches, and for almost all of them, except for one, the full precision vectors are doing better for this particular task. And everything is actually trained on 2017 English Wikipedia with a window size of 10 and the number of negative samples being 12. They ran some extrinsic experimentation for a question answering task. And they used an algorithm introduced by Facebook that is publicly available for question answering. And they used a labeled data set, Stanford question answering data set. And they tried full precision quantized vectors, and you can see that the best result is achieved again by quantized vectors. And in general, they're doing better than the full precision vectors. So even though these vector representations take a lot less space, storage, and memory, they're doing better on at least two of the tasks they're evaluating them on. So the other experiment they ran was to see if they're prone to overfitting compared to the regular vector representations. So here, based on as the number of epochs increases, you can see that the blue one is actually the quantized version of the vectors. You see that the loss goes down and the accuracy increases. Okay, but for the regular and the standard vector representations, the loss goes down, but the accuracy first it goes up and then it starts going down. So they concluded that actually these quantization functions act as a regularizer that would prevent your model from overfitting compared to the standard vector representations. Same for vector dimensions. As you increase the number of dimensions in the vector, for the quantized version of the embeddings, the loss decreases, the accuracy increases. But for the standard version, the loss goes down, but the accuracy, it increases a bit first, but then it goes down. So it overfits. Okay? They do produce a lot of visualizations also as a way to show that the method works. And this is actually for the word similarity task. For each word, they take the nearest neighbors and the furthest words and visualize them. And you can see this is, I think, a 1-bit quantized vector. And you can see a but kind of a pattern here. And it's just noise here. This is the same for a sport. You can see that these vectors are very similar for the nearest neighbors, but these ones, like, you don't see any pattern whatsoever. Okay? There are a lot more in the paper, and also the code is available on GitHub. So you can have 1-bit quantized vector representation of words that do even better than the standard representations of these vectors on certain tasks, and they take a lot less storage and memory, again, if you need to have them on a mobile device or an IoT edge device or something like that. And as I mentioned, you can find the code on GitHub, try it out. I believe it is written in C++. And that brings me to the end of this presentation.